Our main goal is to understand how irradiation and corrosion act synergistically to impact the evolution of a material. And the premise is that irradiation or corrosion by themselves behave one way, and when you couple them together at the same time, a material is going to evolve in a new way. And our goal is to understand the fundamental mechanisms by which that material interacts with the radiation and corrosion environment. So Future is a partnership between 2 national labs, us and Pacific Northwest National Laboratory, and 5 universities. So we have Berkeley, North Carolina State, University of Virginia, Bowling Green State University, and University of Texas, San Antonio. And it's this collection of partners, this collection of expertise that allows us to target this complex problem. Some of the most interesting things that we've learned is that irradiation and corrosion, that synergy depends on the material system and the environment we're thinking of. So we've seen in some cases that irradiation can accelerate corrosion, so it makes the problem worse. We've also seen scenarios where radiation actually slows down corrosion and maybe makes the problem better. And so there's a lot of complex physics going on here depending on the material and the corrosive environment. And we're just teasing out now some of the fundamental reasons for that and how that relates to, for example, the heterogeneities, the material structure, the materials chemistry that we're placing in these corrosive environments.
The kinds of simulations that Future do range down from the atomic scale, where we study the properties of individual point defects created during irradiation, all the way up to larger bulk grain scales, where we study the way that those point defects accelerate and change the way that mass transports around the material system. Simulations are advancing the Future project by helping us understand and systematize the knowledge that we get in the experiments much better. This is going to make it easier for us to understand what's actually going on and identify which mechanisms are active better than we could just from the experimental data all by itself. We have an ability to couple all the different possible charge states that a point defect could have in an oxide together and dynamically solve what those charge states are on the fly, and also represent how that changes the flux of point defects through a growing oxide scale during corrosion.
So over the years, ion beam has been matured to mimic what neutron can do in the reactor settings. My lab, Ion Beam Materials Laboratory, I would see is one of those pioneer labs dedicated to the materials research. And we have expanded some capabilities over the years. And I see the more quantum-related research will use ion beam, not just use ion beam to produce the defects, it also use ion beam to dope the 2D materials to produce new color centers or to produce the new photon centers for the optoelectronic applications. Another area of ion beam is to expand into the fusion research area, trying to coupling the plasma device with the ion beam, trying to mimic what's happening in the surface region of the plasma material interactions. So that's a few areas I think ion beam can continue to contribute to the future research in this area.
Thin films are coating materials that allow us to combine the surface properties of some materials with the bulk properties of other materials. So we find thin films on your glasses to protect them from scratches and abrasion. We also find them on things like your iPhone to make them different colors. Thin films allow us to model those materials that are found in reactor-type environments. So it's a high throughput synthesis route that allows us to change a number of microstructural and chemical features of a material to simulate those materials in a reactor-type environment that are exposed to corrosion and irradiation. So in future, we're trying to study those coupled extremes of irradiation and corrosion. These high throughput synthesis methods allow us to change a lot of different properties in the material to see how those materials respond to those two coupled extremes. What we found in future thus far is that the initial defect structure in these materials is vitally important to determining how they respond to these coupled extremes. So what we study specifically is how that initial defect structure, so say voids or pores in the material, affects that irradiation and corrosion process. So one of the things that we found in our studies is that we can actually control that defect structure using our synthesis technique.
Positrons are useful in material science because they offer us a way to look at defects at a fundamental level. We have the ability to find one missing atom out of 10 to the 7 atoms with positrons, and this gives us the ability to study defects right from their formation, from looking at monovacancies up to few atom clusters of vacancies. We can really develop an entire picture of how defects are moving throughout a material. Positrons are the antimatter version of an electron. They are the same size, but the opposite charge. The goal of the in situ positron experiment is to get a fundamental understanding of how defects evolve, not only before irradiation, not only after irradiation, but during irradiation. The positron experiment is related to the future project because it provides insight into the radiation resistances of materials that are studied in the future collaboration. The positrons are useful for studying how radiation damage plays a role in novel materials and as well as fundamental ones.
So the purpose of the irradiation corrosion experiment is to study materials' behavior under simultaneous extremes like irradiation and corrosion, so that we can better understand how to design materials for nuclear reactors. So when materials are exposed to multiple extremes, the effects of those are typically more than just additive. And so we're trying to understand what happens in a real system like a nuclear reactor when both of these effects come together. In future, the irradiation corrosion experiments is one of the major experimental efforts that we have. When irradiation and corrosion come together, the assumption that we're making is that the two are more than just additive. So we're assuming that irradiation exacerbates corrosion to an extent, but there is exciting recent research that has shown that sometimes that's not the case, and we actually see that corrosion is slowed down by irradiation of the material. But that only happens when both of these are simultaneous.
The most important thing that Future has discovered so far is that radiation and corrosion interact differently depending on the material and the environment. So for example, we've seen that irradiation can slow down corrosion. We've also seen that it can enhance the rate of corrosion. So it's really a complex problem where it really depends on the material, the corrosive environment, the conditions, and the details of the chemistry and microstructure of the material. Going forward, what we're trying to understand is how all those interplay and trying to build a fundamental understanding so we have at least some predictive understanding of what's going on when a material is exposed to corrosion and irradiation at the same time.